Are present here. So we are moving on to the third session of day 2. So today we have our resource person Dr. Praveen A.S., who is going to talk about the 3D printings in the ceramics. Let me invite Rakesh for the felicitation of the resource person.
Good afternoon, one and all. I'm having a great pleasure to introduce Dr. Praveen A.S., who is an associate professor of the Department of Mechanical Engineering in World Tech University, Chennai. He completed his BTech in Mechanical Engineering and MTech in Machine Design from the University of Kerala. He graduated PhD degree in July 2016 from the Department of Mechanical Engineering in the National Institute of Technology, Trichy, for the title Experimental Investigation on Erosion Wear and Oxidation Behavior of Nickel-Based Thermal Spray Coatings. His research interest includes tribology, thermal spray coatings, and additive manufacturing of ceramics. He has an experience in developing various composite coatings for erosion, wear-resistant application using thermal spray techniques and microstructural and mechanical characterization of the coatings. Recently, he developed ceramic structures using direct link writing, the 3D printing technique, which has the potential applications to aeronautical, automotive, electronics, and medicinal domains. He's having a teaching experience of 6 years and a research experience of 3.5 years. He has published 12 papers in reputed international journals like Ceramics International, International Journal of Refractory Materials and Hard Materials, Applied Surface Science and Materials Research Express, and published one book chapter in the Elsevier reference module in Material Science and Materials Engineering. His research H index is 6 and the total number of citations is 160. Also, he is acting as the reviewer for Elsevier journals such as Ceramics International, Journal of the Mechanical Behavior of Biomedical Materials and Materials. So I welcome you for the section and we wish that the section will be a wonderful one. Thank you.
Yeah, thank you, Rakesh. Thank you for the nice introduction. And so am I audible to you?
Yeah, it's audible.
Yeah, and very good afternoon to all the participants. And first of all, I would like to share my uh, happiness with you for inviting me for this FDP on IoT-based manufacturing and design. And so I'm very happy to share my knowledge and my experience in 3D printing. So just yeah, is it fine? My video is fine.
Yeah, it's fine, it's fine.
Okay. Uh, in this talk, I would like to share my experience and learning, which I gained over the last 2 years on 3D printing of ceramic materials. And here, in the first phase of my presentation, will cover the different types of additive manufacturing or 3D printing we call it as. And the second phase will be covering with the direct ink writing of ceramics, which I'm doing in our Weldtech lab. So let me share my screen. I hope that my screen also visible to all the participants. So
yes, sir, it's visible. It's visible.
Yeah. Okay. So before going to the presentation, I would like to ask the basic question: how do we make things? So it means if we have a bulk of material like this or chunk of material like this, how we are going to convert this to a useful product like this? So for that, we have a basically there are three manufacturing process. The first one is called as formative manufacturing process. And then the second one is the subtractive manufacturing. And the third one is the latest and disruptive technology we call it as additive manufacturing technique. Okay, so now we'll look into these three for to get the link to my presentation. So let's see what is subtractive manufacturing process. In this, we will take a bulk of material and using some specific tooling, we will remove the material. That's a subtraction. We will remove the material so as to get the desired shape and size. Okay, here we need some specific tooling as well as means different types of tools we have to use as well as different types of fixtures. That's a in order to get the final products. And let's see the second type of manufacturing process, which is called as formative process. This is a all technology, the centuries all technology. The first one is the forming process. Here you can see is the forging technique. In forging technique, what we'll do, we'll take the bulk material with the help of heat or without the heat. It's called a hot working or cold working. We will apply the force and accordingly we will get the desired shape. And the another type is the casting process. So in casting process, what we'll do, we'll pour the molten material into a cavity. So cavities which has the desired shape, and the molten material is allowed to solidify in the mold, and we'll break the mold so as that we'll get the final and the desired shape. So these are the conventional manufacturing process, very centuries old process. So here in the recently the additive manufacturing, that's a the recent technology, or we call it as disruptive technology, has gained a lot of attention among researchers and academicians because of easiness in developing complex shapes. So whether should we replace the other two processes, but means the subtractive and the forming process? The answer is no. So that will I'll cover in the subsequent slides. Okay, so additive manufacturing, as I mentioned, it's a layer by layer deposition technique. So for that, we should have a CAD data or a digital data. From that, we are developing the desired shape and size. And when and so there is a confusion between whether this additive manufacturing and 3D printings are similar or they are different, or whether they are interchangeable. So as per the ASTM standard, they have given the definition for additive manufacturing as well as 3D printing. So let's see what is the definition given for the additive manufacturing process. So it is a process of joining materials to make objects from 3D model data, that's a digital CAD data, usually layer upon layer, as opposed to subtractive manufacturing methodology. Now see what is 3D printing. So 3D printing, they have given definition like the fabrication of objects through the deposition of a material using a print head or nozzle or another printing technology. So I would say with additive manufacturing is the broad way of technique. All the process will come under this additive manufacturing classification. I would say additive manufacturing means what is the difference between additive and the 3D is that in additive we are not going to use any print head or nozzle. So that is the basic difference between additive and 3D printing. So whatever it is, nowadays the researchers or the industry person are using additive manufacturing as 3D printing as interchangeably. Okay, so there is nothing wrong in mentioning additive manufacturing, or you can use it as a 3D printing process. So, and when you have to select the additive manufacturing process, this is really big question. So whether we have to go for additive manufacturing or we have to use the conventional technique like formative or subtractive technique. So or the question is whether we can replace this formative and subtractive manufacturing, or we can use all the process with the help of additive manufacturing. The answer is no. So from the graph we can see that, so when you want to produce a high volume of components, or you can say thousands of components, uh, we have to go for the formative. So in the formative and subtractive, the dimension or size and shape of the product or parts to be very simple. So there we have to go for the formative or subtractive manufacturing. Subtractive manufacturing is suitable for when it is 100 numbers part. Okay, so additive manufacturing is very attractive in the case where we need to develop a complex design or complex geometry at very low cost. So that's why additive manufacturing is widely used in biomedical application, where we need to develop any implant or any scaffold with complex design. Means complex design in the sense where we need a very the minute pore size, which will which will enable the cell growth inside the pores, and these pores should be interconnected and with a good mechanical characteristics. That's why with this additive manufacturing is very widely used in biomedical applications. Okay, so now it's clear that when you have to select the additive manufacturing technique. So now let's see what are the advantages and disadvantages of additive manufacturing technique. So I'll start with these two examples. Here you can see the G fuel nozzle. Here you can see this first one is the G fuel nozzle, and the second one is the aeroplane seat buckle. Okay, so initially, the G-Ware fabricated this part using conventional process like fabric. It's made up of different parts, like 20 number of parts were there. They assembled using welding so as to make a single component. So with the help of this additive manufacturing, they were able to make this component as a single component. Thereby, they were able to reduce the weight of the component by around 25%, and so that they could achieve a cost efficiency of 30%, and they were able to achieve inventory. That means here there is no inventory cost, so inventory cost around 95%. Okay, so from this example itself, we got what is the advantages of additive manufacturing. And the second one is the aircraft seat buckle. Initially, so you just this seat buckle is belongs to an Airbus 380, which is having a seat capacity of 853, and initially this the conventional steel buckle is having a weight of around 150 grams. So with the advantage, with the help of additive manufacturing technique, they were able to produce a structure like this, any seat buckle like this with biomimetic structures, and they were able to reduce the weight of this component by around 50%. So initially it was 150, now it's become 75. So thereby, what is the advantage is that they could reduce the weight of the aircraft by around 70 kgs, so that they will get the fuel efficiency, means fuel saving and also be improved. So that's a one of the application of additive manufacturing technique. And so, as I mentioned earlier, additive manufacturing is widely used uh, for developing complex parts. Okay, that so means 3D printing has the flexibility or freedom to fabricate the complex shape and size. And the second one is the rapid prototyping. So rapid prototyping means you can save or you can save the prototyping process with the help of 3D printing. In the conventional prototyping means if you want to change any design, means you have to make the mold as well as the casting. You have to redesign the mold as well as the casting. Here we can directly print, and we can see that how it looks like according to the your geometrical dimensions. Okay, and the third advantage is minimizing the waste. So we can see that from the left side figure, there is a comparison between subtractive manufacturing process and additive manufacturing process. We can see the waste of the material. So suppose if you want to make a component with 10 kg, the final product weight is 10 kg. You have to start with the starting material of 100 kg. But in the case of additive manufacturing process, you may have to start with a spool of material or a powder material from 10 kg, or sorry 15 kg, so as to you can, so that you can make a 10 kg product. So this factor will play a major role in the case of aircraft industry, where they will be seeing flight to buy ratio. So flight to buy ratio is nothing but amount of material used, starting material used for fabricating the final product divided by the weight of the final object. So, so with the help of additive manufacturing, we can minimize waste of the material. Okay, and in the additive manufacturing, another thing is that the we have to go for the post processing operation to remove the so because in additive manufacturing process, the product which are developed will have the poor surface roughness. So we have to improve the surface roughness by using some chemical softening or um, uh, any of this abrasive water jet machining process to impart the better surface finish. And also it's a cost effectiveness in the sense it's a single process. So there is no any secondary process associated with additive manufacturing except this finishing operation. So it's a directly you can produce the parts so that we can reduce the costs. So, but in the case of any conventional machining, we have to go through the series of operations. So series of operations at different machines. So that will include the that will reflect the cost of the product also. So then let's see what are the disadvantages. Each process has their own advantages and disadvantages. Now we'll see what are the disadvantages of additive manufacturing process. So in the additive manufacturing, so we have a restricted build size. In the case of if you take a fuse deposition modeling, the bed size may be 100 mm into 100 mm, or it can be go to 200 into 200. So what happens if beyond this size? So we have to print the part in one or two steps, part by part. Then later we have to assemble the part. So that's the disadvantages of additive manufacturing. It's restricted with the build size. And another one is the limited material. So here there is a material flexibility is not there. So we have to use the material which are available in the market. So nowadays there are a lot of research going in the area to develop new composite material so that we'll get the properties of both. If we are combining metal and ceramics, we'll get the both properties. So like that, there are a lot of research going on. And also see these companies which are supplying these 3D printers, uh, they'll give the some powders along with that machine. So that powders are proprietary items, so we cannot use any other powders. Okay. And the third one is the, as already mentioned, is the 3D printing is associated with the post processing. It means if you want to improve the surface roughness of the printed part, because the surface roughness or surface topology of the additive manufacturing process is very poor. So we need to improve the surface properties, means the surface roughness, by using some post processing techniques like chemical sorting and any water jet abrasive process. And we started the discussion with the quantity which are suitable for additive manufacturing. As obviously this technique is not suitable for large volume of production. Okay. So we have covered the advantages and disadvantages. Now let's see how the generic process flow of additive manufacturing. As I mentioned earlier, additive manufacturing is a process in which we will have a digital data or any CAD data. We develop, we will create it in the any solid, any 3D softwares like CATIA, ProE, or SolidWorks, etc. And that will be so first we'll create the CAD model, then we will take the geometric data of this part which is to be fabricated. We'll convert it as an STL file. STL is nothing but standard triangular language, or stereolithography language also we can name. And this will be, so this contains the data of its geometry, surface geometry, in the layer by layer fashion. And these data will be imported into a slicing software, where the geometry is be sliced into different layers according to your input data. If you want to print a part with a layer thickness of 0.8 to 1.2, you can define all the features in the slicing software. So there are different types of slicing softwares are there, Cura, Printforce, Slice 3R, etc. And so these softwares of free, we can which are available in the website, we can download it. And so these slicing software will define the tool path, so how the tool has to move, means the print has to move based on the geometry. And next, these data, this will be in the G code. G code will be fed into a 3D printer. So here you can see a FDM printer. So we have to do some initial setting for the printer, like we have to load the filaments, and we have to clean the bed surface, and we have to define the printing speed. So, but in the case of laser or powder bed technique, we have to define the laser power and laser diameter and hatch distance, everything we have to define in the printer. So we have to have some machine setting. So then these G code will be sent to the 3D printer. So that according to the G code, your final product can be developed. So this is the generic AM process. Whatever the process, whatever the technique we are using, this will be your generic process. So as I mentioned, so how we are creating CAD model with using some 3D software. So, but in the case of biomedical application, so we have to create the 3D data or 3D design from the MRI scan or CT scan data. So the output of this MRI and CT scan will be in the DICOM file format. So using some softwares like Mimics and ITK NAP, we can convert these 2D data into a 3D using Mimic software, which is expensive. So you can use ITK Snap for free. ITK Snap is the free access. You can use it, but the resolution of the part will be poor in the case of if you are using ITK Snap. Okay, so now next we will cover the different types of AM process as per the ASTM standard. So these are the 7 classification of additive manufacturing process. The first one is the binder jetting process. The second one is the powder bed fusion technique. The third is the material jetting process, and the fourth one is the material extrusion technique. So in this talk, I will be covering the material extrusion technique process called direct ink writing of direct ink writing. Okay, and the fifth one is the sheet lamination technique, and the sixth one is the VAT photopolymerization, which is very old technique, and the first 3D printing technique is based on the VAT photopolymerization, and the last one is the direct energy deposition technique. Now let's see how this process works and what are they, how and video of that each process also I'm going to share. And the first process is the VAT photopolymerization. So in this, what we'll do, the VAT is nothing but it's a large container which is having a polymer. Okay, so this technique is suitable for the photosensitive polymers. Okay, so here you have a vat which contains the polymer, and these polymers will be exposed to a light source or any laser. So according to your design, your object. Okay, so your part, which part you want to fabricate, so this laser or any light source will move accordingly. Okay, so here you can see a fabrication print platform, and this is the liquid photopolymer. When it is exposed to light, it will get solidified. Okay, so I will share the video so that you will get more understanding. So this is the vat which contain the photosensitive polymers. Okay, these polymers will be traced or exposed with the help of a laser or any lighting source. So here you can see a laser source. So this tool path will you can define using some slicing software. Okay, so after printing first layer, this bed will move down to the vat or photopolymer, and there is one roller is used to level the resin. Okay, and this process continues so that you will get the final process. So if you have any supporting structure in this, we have to go for some post process to remove that support structure. Okay, so the second process is the material extrusion process. So this one, I think all the participants have familiar with this material extrusion technique. So you can take the example of fuse deposition modeling. So all the 3D printer which are available in institute are made up of this technique. Okay, so material extrusion. So this technique is called material extrusion. For the specific name, we can call it as fuse deposition modeling or contour crafting. This is used for civil constructing the building. For constructing building, the cement and mortar will be laid in using a contour crafting technique. And also another name for material extrusion process is the robot casting, or we can call it as direct engraving. Here, what is the starting point of the process is we will take a material in the form of a wire, okay, or we can call it as filament, or that filament is made up of thermoplastic materials like ABS, acrylobutyl nitrate, and uh, uh, polylactic acid (PLA). And there are different varieties of polymers available, so we can which are suitable for fuse deposition modeling. So here you have a heated nozzle at which the filament will be melted, or any semi liquid form will be generated, that will be deposited to the print bed. So the print bed you can either keep at room temperature, or you can maintain at the high temperature. For ABS, we have to maintain the bed temperature around 100 degrees. So these the heated nozzle, the temperature of the heated nozzle will be in the range of 210 to 250, at which these polymers will get melted. Okay, and after depositing, the immediate solidification of this polymer takes place, and also the fusion between the subsequent layers, the two printed layer takes place, so that you will get the final object. Okay, let's see how it works. So this is the starting point. We'll make the material which is to be printed in the form of filament. Okay, it can be either metal or it can be a polymer. So it is not a pure metal, it may be binded with the polymers. Okay, this is the heated nozzle. So at this location, this is the filament. So here we'll apply the temperature which is suitable for melting the polymer. And this print head will move according to your slicing software. Okay, this is how material extrusion process. So in today's talk also, I'll be explaining about the material extrusion technique called as direct engraving. So the third process is the directed energy deposition technique. Here, what we'll have is a laser beam. So that's a heat source. It can be a laser or any electron beam. Okay. So here we'll use a coaxial nozzle through which the sender, the power source will be emitted, or any heating source will be emitted, and through the coaxially the powder material will be fed, so that this laser will melt the substrate as well as this powder, and it will be deposited according to your movement of the laser head. Okay, you can call it as a print head. So this technique is widely used for depositing nickel-based high performance metals. Okay, any titanium polymers. Polymers are not pure polymers. Polymers with a ceramic material which are feasible in this technique. It's like a welding process. We'll see that how it works. So this is the nozzle. This has a provision for uh, um, a laser as well as powder. This is a coaxial nozzle. So through the center, laser will be coming, and through this coaxial, the powders will be ejected. So at this location, this laser will interact with the powder, and so that melting of the powder takes place, and melting of the substrate also takes place. And after this solidification, once the laser moves away from that printed location, it gets solidified so that you will get the final product. So here we are using the laser power source. And what is the difference between laser power bed and this one? So here we don't have any powder bed. The powder is fed into this nozzle with a separate feeding mechanism. Okay. So these techniques are widely used for super alloys, high temperature performance um, um, materials. The next technique is the material jetting process. In material jetting process, what we'll do, this is also similar to direct ink writing. So, but there is a difference between there is a difference in the ink formulation. So this technique is same as the our 2D inkjet printing or normal printing process. So here first we'll make the ink with the suitable binders and binders, like when it is exposed to a UV light or any laser, it will get solidified. So we'll make a this is suitable for metals, ceramics. So we'll make ceramics mixed with some polymers. So that will be injected to a injected through a tiny nozzles. The series of nozzle will be there. So this is normal to how normal printer is working. Um, Injected according to your part um, design. Okay. And after printing each layer, this will be exposed to UV light so that the solidification of the part takes place. Let's see how polyjet works or material jetting works. So here we have a series of nozzles through which the material which is to be printed is ejected. Okay, so either you can use a thermal ejection system or any pneumatic ejection system. The ejection will based on your data, CAD data or a slice data. So let's see, the next process is the binder jetting process. So binder jetting process is also is a powder bed process. Here we see we have a two powder containers. The first one is the powder supply container, and the second one is the fabrication or a build platform, or we can call it as fabrication platform. So what happens? So the part which is to be fabricated is will develop at the fabrication platform. So how it works? So here the fusion of the powders, it takes place with the help of a suitable binder. Okay, so the gluing of the powders takes place with the help of a suitable binder. So that binder will be injected to a suitable inkjet print head. Okay, so here you have a two compartment. One is called fabrication platform, another is a supply tank or any powder supply platform. So this inkjet head will move according to your your object geometry, and after printing first layer, what happens? This fabrication platform will move down as per the your slicing software. So if you made a 1 micron or 1 mm, it will move that much down, and this powder supply tank will move 1 mm or whatever according to your layer thickness. And with the help of a layer, we will spread the powders to the fabrication platform, and subsequently the next binders will be injected on the powder bed, so that the fusion of the powders takes place according to your geometry details. So there is a similarity between binder jetting and the laser powder bed technique. So there we'll use laser instead of this binder. Let's see how it works. So first we have to start with the CAD model. We have to slice it, and so this is the powder bed. So this is the inkjet head. Okay. So this is the roller which will used for leveling the powder. So powder will be supplied from the supply tank, and after printing one layer, this bed is lowered according to your layer thickness. Then new powder will be poured into the build tank with the help of a roller. So this process continues until you will get the required object. So this is the binder jetting process. So next one is the powder bed fusion technique. So this is also similar to binder jetting process. So there we are applying binders for the fusion of the powders. So here we are using laser source for the fusion of or binding of the powders. So this working is same as, but there we have a limitation of the material to be used. Here we have, so this is the one of the prominent technique we are used for fabricating most of the component. Okay, so here there is only limitation is that uh, here we have to use the material, the machine is expensive, and we have to start the material in the form of powder form. So there we have the characteristics of the powders also very important. So if the powder is spherical, then only that packing density will also more. And nowadays they are trying to develop some bimodal particle distribution. So in order to have a good compaction, particle compaction, and if the particle is in angular shape, the flowability of the particle on the smooth, so that this may leads to a defect in the parts. So that the main requirement is that the particle should have the good flowability. So then only you'll get the defect free parts or components. Let's see. So as I mentioned, this has a powder supply tank, and we have a laser source, which will be directed with the help of a galvano motor system. with the help of a mirror. And after printing first layer, this build platform will move down, and with the help of a roller, we will fit a new powder layer onto the printed layer. Okay. If any excess powder is there, it will be collected at the collection tank. So, the last one is the sheet lamination process, in which we'll take the starting material in the form of a sheet, which will be embedded with the help of in form of metals or ceramic or polymers. And this process is the lamination, stacking of layers. Let's see how it works. So here you have a rollers on which we will these are the 4 rollers which will be used to um, feed the stock material. Okay, so and this will be the initial step. Then with the help of a laser or with the help of a mechanical cutter, we will cut the sheet according to our requirement. This is the first layer. So this heated roller will be used for ensuring the adhesion between two successive layers. So here we are using laser, or it can be a mechanical cutter also. So the laser will cut the required shape. Okay. Then after that, this printing bed will move down, and the roller will rotate, and the new material is formed over the cutted material. Okay. So with the help of the roller, we are ensuring the adhesion between, there is a proper adhesion between the two successive layers. So this process continues until you will get the final object. So these are the 7 classification of 3D printing process. And so I'm sure that with the help of these video, you will be able to understand different types of AM process. So why I'm explaining this is in order to give the link to my presentation. So my presentation is on the directing writing. So in order to understand that, so I have explained all these basics. Okay. So now let me go to the second phase of the presentation, which deals with the directing writing techniques. So directing writing technique is nothing but it's a, so what we have seen is the material extrusion process. This process will comes under the material extrusion based additive manufacturing process. So here, so the other process like a fuse deposition model also coming under this. I will explain what is the difference between directing writing as well as the fuse deposition model. So here the starting material is in the form of a liquid phase material, or we can call it as an ink, or you can say it as a paste. Okay, that paste will be extruded through a suitable dispersing mechanism. So through a nozzle of diameter, so we are using 0.6 to 1.2 mm size. Okay, so which will be extruded through the tiny nozzle based on your CAD model or a data. Okay, so why I'm preferring, so my talk is on directing 3D printing of ceramics. So you know that ceramics are widely used in aerospace and in biomedical, in electronic industries and all. And because of its excellent mechanical properties and thermal stability and chemical stability and all. But the processing of ceramic, the conventional processing, like we will take it in the powder form, we'll mix it with a binder or without binder, and using some spark plasma sintering or any pressing process, we'll adopt to develop the final part. And also we'll use gel casting and tape casting for the fabrication of ceramics. Okay, but the disadvantage is that there we cannot go for the we cannot fabricate the complex shape which are which are required for the biomedical application. As I mentioned, so for biomedical application, so the scaffold implant we are fabricating should have some porosity in the range of 50 to 60, and different pores shape and pore size, and these pores should be interconnected, and that we cannot fabricate in the conventional techniques. But using adopting this 3D printing technique, we can develop that kind of structure. I will show you what are the structure we developed at the Weldtech. Okay, so this is a starting point. Here, the main challenge is that we have to prepare a suitable ink for direct ink writing. If you fail in the ink preparation, we won't get the expected dimension and size, shape, everything. So in this second phase of my presentation, I will be covering what are the required characteristics and what are the how to prepare the slurry, what the rheology required for printing as a best structure. So this will be covered in this talk. Okay, then as I mentioned, this direct ink writing as well as fuel deposition modeling, both are same, will come under the material extrusion technique. So if you want to make a ceramic in FDM, what we'll do, we have to make a material in the form of a filament. Okay, spool. So there we have to mix the ceramic with the suitable polymers, and we have to suitable extrusion mechanism we have to use to get the suitable filament. There the challenge is that the binding between ceramic and the polymer is the challenging. So and the temperature to be applied, that is also challenging. So what happens in the direct ink writing is, as I mentioned, we will prepare the suitable slurry, or we can call it as paste, or it can be ink. Okay, that ink will be extruded through a tiny nozzle uh, based on your part geometry. Okay, in this direct ink writing, we can generate these kind of lattice structures or a spanning structure also. But this retention of this structure will completely rely on the rheological properties of the paste. So because the rheology will determine the output that the required will depends on your dimensional accuracy of the printed part. Okay, uh, I'll show you how it works. So I hope that all of you can see this video. This is the printing machine we developed at Weldtech, and as I mentioned, this is the ink we formulated. And that ink will be ejected using a suitable dispersing mechanism. So this layer by layer deposition takes place. This layer by layer sequence can be defined in the slicing software. So this is not the best slurry we prepared. So here you can see the spreading of the printed line. So that means this ink is not having sufficient yield stress to retain its shape. So this to have some clarity about what is direct ink writing. Okay, the spreading of the ink takes place. So the main challenge is in direct ink writing is the preparation of the ink and its rheological properties. Okay, so and after printing the ink, so how we are dispersing that ink. So there are two types of techniques or two types of systems are available. The first one is the pneumatic system, and the second one is the mechanical system. In pneumatic system, what we'll use some air pressure to eject the prepared ink. Okay, and the second type is the mechanical system. The mechanical system, what we'll do with the help of a stepper motor, we'll actuate this piston, and so that it will apply the pressure on this ink, and this ink will be ejected. The third means this is also the screw type also will come under the mechanical, but here you can see with the help of a screw, with the help of a screw we are transferring the material or transferring the ink from the inlet to the exit of the nozzle. Okay, so this advantage of the screw type mechanism is that here we can precisely control the flow of the material. But here, why it is here the contact between the screw and the material is less compared to other two process. Here this contact is taking place entirely on the this ink base top surface. So here we cannot control it precisely, but in this screw mechanism we can control the flow of the material precisely. So but the disadvantage is that mechanical system is a complex one, and also there is lot of losses associated with the friction. But we started our work or research with the pneumatic based dispersing system. So now we are looking for a piston based. Why it is so? We experience lot of difficulties when you go for the high solid loading ink. So means ink with a high solid weight percentage. So that are very difficult to extrude to the pneumatic system. But with the help of a piston, we can extrude the high solid loading material also. So now our target is on our focus is on the piston mechanical extrusion system. Okay, so uh, we fabricated this 3D printer 2 years back with the help of UG students. So they did this work as a part of their final year project. So what we have done is we converted normal FDM printer into this extrusion based printer or directing writing printer by simply replacing the heated nozzle. Instead of heated nozzle, so as I mentioned previously, we are using a pneumatic based extrusion system. So here we can see this is a piston, sorry, this is the barrel which will have a piston like this. So with the help of a pneumatic or air pressure, we are applying pressure on this piston so that that pressure will be transferred to the ink so that the suitable dispersion of the ink takes place. We can use different kind of nozzle. The selection of nozzle will depends on your ink viscosity. Okay, so here you have a pressure control unit to control the, or you can adjust the pressure so that the smooth flow of the material takes place. Here we have a belt table, which is a built platform, and you have a control unit where you can control the feed rate, bed temperature, and all the things. Okay, so those who are looking to work on this ceramic fabrication, so developing ceramics through 3D printing, they can simply adopt this technique. And this is a complete representation of the printing process. So what we'll do is the starting point is the CAD model, or the CAD model will so the part which is to be fabricated, we'll make it as a in the any CAD modeling software. Then that will be sliced using any slicing software. That will be fed into this control unit, and this dispersion of the slurry will also be controlled with the help of a pneumatic or air pressure. So this is a schematic representation of the printing printer which is available in Welt. And so as I mentioned earlier, the challenging is that the preparation of the suitable ink. If you are not preparing the ink suitably, then you won't get the exact dimension or intended dimension and size and shape, and we won't be able to produce the pore size, required pore size. The first ink should be, we have to prepare the ink homogeneously, means it should not have any agglomerates and it's free from air bubbles. Even though if there is any air bubbles during filling into the um, barrel, you can just simply tap on it to remove the air bubbles. And the another factor is that the viscosity, that is a major factor which influence the dimension of the printed, we can call it as extruded printed line. So it means we have seen that toothpaste, right? So the when you apply pressure, So the paste which is easily which will come out easily, and it will regain its shape once it comes out. So that means the yield stress is also high. So after extrusion, so during extrusion, its viscosity will get reduced. That's what that is called as shear thinning effect. So when you apply load, when you apply shear, so its viscosity will get reduced, so that the extrusion will takes place smoothly. And after extruding, it should retain its dimension, right? So that it will refers as its yield stress. If it is not retaining its yield stress, that means you won't get the extra dimension. So in that video we have seen that ink is spreading like anything, like due to the gravitational force. So this is very challenging. You have to play with the viscosity of the material. So it will change with the material to material, and with the binder material, and also the solid loading. So that is the third thing we have to consider. So how much oleum or how much solid loading you can go in order to avoid the shrinkage of the printed part. See, after printing the part, we have to, so that part is called green part. That part will be subjected to different kind of post processing, like debinding and as well as sintering. So during the debinding and sintering, the evaporation of the binder material takes place, and this will cause the shrinkage of the printed part. So this can be avoided, or it can be reduced with the help of high solid rating. Usually, based on my experience, we are trying with the solid loading of or volume fraction of around 50 to 80. So if it is less than 50, the viscosity of the ink will be very less, so that the with even without applying the pressure also, the ink will this slurry will come out. Okay. And if it is beyond 80 percentage, so from the literature also, the maximum they tried with the 80 percentage. So so beyond 80 percentage, what happens? That ink may not be extrudable through this your dispersing mechanism. We have to play with the range of 50 to 80 percentage. And the another factor is that size of the particle in the ink, that must be at least 50 times smaller than the nozzle. Though we have to select the nozzle diameter such that it should be 50 times less than the particle size. So for example, if you are using a particle with an average diameter of 150 nanometer, the minimum nozzle size you can go is 7.5 micrometer. So if it is less than that, what happens? The clogging of the ink will takes place at the nozzle. So the ink will not be extrudable. So that's called printability. The another fact is that the printing speed. So we have to select the printing speed such that we should get a continuous deposition of the ink. So here we can see the two the things. So one is called the VR. VR is the translational speed, and with the speed at which the print head moves. Okay, in X, Y, and Z direction. And VE is the material extrusion rate. So at the rate at which the material is extruded through this nozzle. See what happens when the VR, that's the translational speed, is greater when compared to this extrusion, material extrusion speed. What happens is the head will move at a faster rate, so that there won't be any proper deposition takes place. So we will get a stretched and a discontinuous printed line. Okay. And what happens if this VR is less than VE, that is the translation speed is less compared to this material extrusion rate. So means at the particular location, so we will get the more material will be deposited, so that the structure become uneven. Okay, so that we have to play with the, so if it is rely on this material extrusion rate is rely on the pressure at which we are applying. Okay, so we have to find the suitable pressure level, so that this VR, that is a translation speed as well as the material extrusion should match. So at this optimum condition only you will able to get the exact printed line. So let's see how it will be. See, this is the figure A shows the exactly printed line, this the ink is printed at optimum ink property as well as the best optimum printed speed. Okay, you will able to print a line with a continuous line with a good with shape retention. So you see what happens in the B, if there is any air entrapment or if the translation speed is more compared to the material extrusion, you will get a discontinuous printed line this, and also this printed line will get stretched. Okay, and the third case, when the material extrusion is more compared to the translation speed, so you will get a chunk of material like this. So the more material deposition will takes place at single location. And also whenever there is an obstacle in the nozzle also, will get these kind of structure. So the challenge is that you have to develop a suitable ink. The ink means suitable rheological properties, as well as you have to select the suitable printing parameters so as to get the an exact or optimum printed line. So you have to play with the uh, viscosity as well as this printing speed. So as I mentioned, it's a rheological property, that's a viscosity and shear rate. So how it should be, that example is the toothpaste. So during extrusion, when you apply pressure, the viscosity should be reduced, which should reduce. That is called shear thinning effect. Okay, so that will be cause the so that will make easiness in the extrusion. So after extrusion, what happens? That structure has to retain its shape. Okay, so means it should not get deformed because of the gravitational force. Okay, it should regain its high viscosity after extrusion. So this is so means you have to prepare an ink which is suitable for extrusion. So and also it should exhibit these kind of properties. So it should be a viscoelastic material. Okay, so before um, printing that material, you have to verify its viscosity. So what is the shear rate and viscosity and all, we have to verify that. So here on case study I'm showing. So here the bottom one is the material without any solid loading. So there you can see that we are not getting the exact pore size and shape, but with a suitable viscosity we were able to achieve a best structure like this. So you have to play with the its rheological property. And see, if you are not using the proper ink, as I mentioned, this you can observe here, it's a sagging of the structure is taking place, so that the yield strength is low after extrusion. The material is not exhibiting this one viscoelastic properties. So the sagging of the structure will takes place. You won't get the exact you won't able to fabricate the pores like this, or you aren't able to print the lattice structures. So first and foremost thing is you have to play with the ink characteristics. So next, I'll be covering some of the basics of biomaterial. So I'm using this directing writing for developing bioceramics. Okay. So biomaterial is nothing but there are wide range of materials available for biomedical application, polymers, ceramics, and metals. Okay. So each one has their own application. Ceramics can be used for a bond replacement or orthopedic application, and fabricating heart valve or dental implant application. Metals can be used for mostly used for orthopedic application, and widely used is titanium and stainless steel. And for dental application also we are using. And polymers used for drug delivery devices and skin for cartilage printing. We are using polymers. So polymers are not used for orthopedic application because it's a weak in mechanical properties. And also we can combine these materials so as to make a composite material, so that we'll can achieve the properties of polymers as well as ceramic and metals. And so that there is a another important factor is that the material you are selecting for any particular biomedical application uh, should be biocompatible, in the sense that there are some classification based on the host response after implanting any scaffold, any implant into your body. It should not cause any toxicity, or it should not cause any adverse effect to our body. So based on that, we can classify the material as bioinert material, bioactive material, and bioresorbed material. So bioinert material example is the titanium, and stainless steel. So what happens is bioinert, they are biocompatible, but they are not accelerating, or they are not taking part with the cell growth and cell adhesion. Okay, so they will be inert with the with the bio cells. And the second classification is the bioactive material. These bioactive materials are material which will cause the cell growth, will enhance the cell growth, will actively participate with the cell so that the cell will grow over the implant. Okay, so example is all the bioceramics will comes under bioactive material. So aluminum oxide and the zirconium oxide, tricalcium phosphate. Bond is made up of tricalcium phosphate. So these kind of materials are bioactive materials. And the third classification is bioreservoir material. Bioreservoir materials are nothing but, so the material will degrade as with the uh, with the regeneration of the tissue. Okay, the example is magnesium, and some ceramics, cements are also bioresorbed material. And see means the material will, so once you implant implant in our body, or this implant will get degrade as well as at the rate of tissue regeneration. Okay, and we are trying to develop some, so these are some of the biomaterial requirement. So first, the material should be biocompatible, and biocompatible in the sense it should not cause any adverse effect to the patient, or a adverse effect to our biological system. And it should have some adequate mechanical performance. So according to your application, if you are using for orthopedic application, the material will be suitable for withstanding a shock load and all. So we have to verify its mechanical performance, fracture toughness, and compression strength and all. And finally, we have to see that application design. So as I mentioned, this your anatomy of our body will uh, change patient to patient. So if you are developing some scaffold or any implant, that implant should match with the patient. So there we have to play with we try to develop a suitable structural design which matches with the patient. Okay. So finally, after fabricating this biomaterials, so then we have to test it. We have to go through the series of tests, like we have to see the physical properties as well as mechanical properties. Like if you are using it for orthopedic application, what is that compression strength, what is the fracture toughness, that thing you have to verify. And then after passing this mechanical properties, then it has to be go through the biological test. So there are two types. One is the in vitro and in vivo. In vitro, what we'll do in the lab scale, we will test it. And in vivo is the animal study. We will use small animal and a big animal. Small animal, rat and rabbit we can use. And for in vivo, in the large animal models, maybe a sheep or monkey, pig, we can use it for in vivo study. So once it passed through all these tests, then only we'll get the approval for using this kind of material for biomedical application. Okay, so and also we are trying to develop these kind of structures, design of these structures by mimicking the structures which are available in the nature. So one example is honeycomb structure and Venus flower basket. So because these structures have their own high specific strength to weight ratio. Okay, and also they are able to take more load and lightweight. So that's why we are trying to imitate these kind of structure for our scaffold design. So I'll be explaining. So direct thing writing alumna or a direct thing writing tricalcium phosphate. We are trying with these kind of mm, material, and we are trying to develop these structures for, so which is in the initial stage. So we have developed some different structures means we optimize the slurry so that which will become printable. Okay, so for making the alumina ink, what we have taken is, here we have taken PVA material is the polyvinyl alcohol, which is used as the binder, and the water is used as the solvent. Okay. So this will be the gel will be prepared with the help of a magnetic stirrer. So the applying a heat or applying a temperature in the range of 70 to 80, so as to make a PVA gel. So first we have to make a PVA gel according to your weight percentage. So here we have taken 15 weight percentage PVA gel. Okay, that means 15 gram of PVA powder and remaining 85 gram of water. Okay. Then this will be mixed with the alumina powder. Alumina is the alumina oxide. Okay, alumina or any tricalcium phosphate which we are planning to print. So that can be different proportion we prepared. So the suitable preparation, as I mentioned earlier, we have to go for a high solid loading in order to avoid the shrinkage of the printed part. So it can be either 50-50 or 50% of the powder, 50% of the PVA gel, and then 60-40. So we tried with 50, 55, 60. So with the pneumatic based dispersing system. So here we have used the alumina nanoparticle, which is having a size of 45 nanometer. Okay. So first we will make the ink like this, then it will be printed with the help of a suitable dispersing system. So here we are trying to print a rectangular with having with a full 100% infill dimension of 15 to 25. So by applying different condition at room temperature as well as uh, mm, a higher temperature, means a temperature like 115 degrees Celsius to get the better structure. So this is the starting point of our research work. We tried with the different pressure and different nozzles diameter and different feed rate to get the dimension like this. So we tried with the developing of circular structures of dimension 25 mm with different parameters, like we change different parameters like nozzle diameter, feed rate, and pressure. So when the slurry concentration changes, we will get the different structures. Okay, it will vary according to your printing parameters. So finally, we achieved a best structure like this based on this parameter. So whoever trying to develop ceramic is direct ink writing, the first and foremost thing is we have to prepare the suitable ink with a sufficient solid loading, and next we have to see the different process parameters. So then only you will able to bring the uh, uh, optimum structures. So here I'm happy to share that we developed a 0.6 mm thin wall without any distortion. So we tried with a 60 percentage of ink and a solid loading of 60 percentage, and we are able to achieve a thin wall structure of 0.6 mm without any deformation. And now this is a follows part, and then we inside this structure we are trying to develop some different honeycomb structure or rectangular or square structure for a biomedical application. So these are some of the structures we printed here, honeycomb structure. So based on our input, means our ink rheology, ink properties, and process parameters, we develop different kinds of structures like this. So these are the green part. Then this part will be subjected to debinding. So the debinding means we will remove the binders at a temperature of 100 or 150 degrees Celsius, and debinding process takes place. Then after debinding, that these ceramic parts will be subjected to high temperature sintering process. So there also we have to see that shrinkage of this part, whether we are getting the exact size and shape, exact pore size and pore dimensions. So accordingly, we have to see the different sintering process. So how this is going to influence the mechanical properties. These are the work which are planning to carry out in this area. So, and some of the examples I would like to share that. So which are available in literature here. The researchers have developed hydroxyapatite. This is nothing but tricalcium phosphate. So bond is also made up of calcium phosphate. So they developed the lower jaw support. So with the help of robot casting. So you can see the different type pore size, pore structure they have developed. So these pores are required for enhancing the cell growth. Okay, this is one example. So another example is that they have inspired from the cactus leaf structure, 3D structure. So outer surface will be more surface area will be there. So this more surface area will cause the cell to grow more, and it will supply more nutrition to the uh, uh, body. So people are working on these areas to mimic the nature to solve our problems. So this is a honeycomb structure. This honeycomb structure is developed with the help of epoxy-based ink filled with some fibers. So different fibers they have tried, and they have inspired the balsa wood structure, which is a honeycomb structure or some lattice structure like this. They try to achieve this kind of structure for some mechanical application. They in that they achieved a higher mechanical characteristics also. So these are some work which are available in this area, direct writing. Those who are interested, they can also try to develop, because this process is very simple and very economic process, where we don't need any high power laser, high cost laser, or any powder, but we required for creating ceramic structures. So this is another good example of mimicking nature. So this structure is inspired from the lotus leaf root structure. So this lotus root has pores like this. So this can be a, so what they did is, using direct ink writing, they modified the nozzle to develop these kind of structures. So if you use the conventional nozzle, you will get a solid strut like this. So so why we are going for these kind of pores is, which will enhance the vascularization, means the new blood formation, new blood cell formation from the existing cell. So these kind of structures are required for biomedical applications. So these research have developed different nozzle to fabricate. They modified the conventional nozzle to fabricate these kind of strut, like single strut, double strut, and four pores like this. So these structures are ideal for biomedical application in terms of its low density and high porosity and low flow resistance. So this blood vessel will form easily over these kind of structures. See, so all the researchers are working towards these kind of things to develop the best structures, biomimetic structures for biomedical application. So we are also working on that direction. So we are also trying to develop some scaffolds. These designs are inspired from the bamboo tree. The bamboo tree structure is like this. We have a porous structure, the different porous structure will be there. It will be patterned in a hexagon. So based on this, we developed some our own design with a different circular lattice, rectangular lattice, and circular with some fringes, and triangular lattice. And we are trying to, this one is fabricated is the fused deposition model. The next level is we are trying to use the direct ink writing to develop these kind of structures. So we observed a good result for the this one circular lattice. So coming to the end of my presentation, so we have covered different types of additive manufacturing process and its classification. And my intention was to give some insight about the direct ink writing. So why am I focusing on direct ink writing? We don't need any expensive laser, and we don't need any powder bed to fabricate the things. So it's a cheap uh, the cheap and best technique for developing ceramic materials. And you all know that 3D printing has widely used in all the different fields like aerospace, automotive, and biomedical applications also. And nowadays the researchers are trying to combine 3D printing as well as biomimetic design to create new design or new material to solve our day-to-life problems. And this 3D printing has widely used in biomedical application. As I mentioned, it's easiness in developing complex shapes like different pore structure, pore shapes, and interconnected pores we can easily fabricate in the using 3D printing. But the next level is that more the revolution is application like organ printing is going on, but it needs a lot of iteration, and it will it's a time there's a lot of time required for developing these kind of structure. They already printed some so liver and ear using some bio inks, but a lot of iteration and a lot of approvals required for implementing these kind of materials and these kind of techniques. So with this, I'm stopping my presentation, and thank you all the participants for their patient listening. And if you have any, yeah, if you have any queries, you can ask me. So I'll try to give the answer.
Thank you, Dr. Praveen. Thank you for the wonderful presentation. Now it is up to the participant. If you have any queries, please rise up. Participants, it's the time for a question and answer.
Yeah, I'm happy to share that if anyone is interested in developing these kind of printers, so you can write to me. So my mail is already I've mentioned in my first slide, and so this is an emerging technique, I would say that. So anyone, so even you can using this technique, we can print metal as well as.
Praveen, some question is there in the chat box.
So there is a question from Motion Dalvi. That can you share your first slide?
Now?
Yeah, I think the person might be having some clarification or
no, first slide is my title slide, right?
Or for the contact.
Okay, fine. So in all the institute, I hope that all of you having this symbol FDM printer. So in that you can attach this extrusion or pneumatic based printer to make it work on more on complex ceramic materials. We can do like that. But if in FDM only limited, we can go with the this one polymer material, which are not suitable for biomedical application or any high temperature application.
So if no other question, let me wind up. Let me ask Rakesh, Mr. Rakesh, to conclude this session.
So good evening, everyone. Okay, it has been a great pleasure by since we are receiving we are hearing a talk by Dr. Praveen after a long time, and it gives me more privilege because I was a colleague for ex-colleague of Dr. Praveen. And thank you, sir, for detailing the various aspects related to the 3D printing. And I think you have made this section very beautiful by explaining the works which you have done related to the 3D printing, the use of ceramics and other techniques. And many of your trials were also detailed during this section. I thank you, sir, for the wonderful section. And I hope all of you have enjoyed, or all of you have gained some sort of knowledge regarding 3D printing. And it gives me another one pleasure to explain to you that we had Vishyoti College of Engineering and Technology had participated in an international event in which we had developed a prosthetics amp for a handicapped person, and we were ranked at ranked at the 9th position among 150 universities all over the world. So thank you, and I thank you all of you for your wonderful participation. Thank you, sir, for the wonderful speech.
Thank you. So I can leave the meeting, right?
Yes, sir.
Sir, Praveen sir, can you just look into the chat box? There's anyone coming for you.
Chat box. Yes.
Yeah, you have a comment from one is Motion Dalby. Shall I read it?
Yes, I can see the last one, right? Thank you, sir. It was very exciting to hear about additive manufacturing being used for biomedical applications. So it's just a common, right?
Yeah.
Okay. Thank you.
Okay, sir. Okay, Dr. Praveen. Thank you. Thank you very
Okay.
much.
Thank you.